Welcome back, design junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. Imagine you're sitting in a window seat on a commercial airliner, right? You're cruising at, say, 35,000 feet.
Right, way up there.
Yeah, and outside, it's like negative 60 degrees Fahrenheit. But inside, you're enjoying a lukewarm coffee, totally comfortable in this pressurized cabin.
Best place to be.
Exactly. But I mean, right between you and that freezing, totally oxygen-deprived void is a sheet of aluminum alloy that's barely thicker than a few credit cards stacked together.
It's actually terrifying when you really think about it.
It is, because with every single flight, that cabin is pumped full of air, like a giant metallic balloon which stretches the fuselage, and then it's depressurized upon landing, relaxing it. So over years of service, that thin skin expands and contracts tens of thousands of times.
Tens of thousands.
Right. So how does the plane know not to just tear apart? Like, how do the engineers who built it actually guarantee that microscopic defects in the metal won't just suddenly link up and, unzip the aircraft at altitude?
Well, that's the multi-million-dollar engineering question, isn't it?
It really is. So today, we are taking an absolute masterclass in the unseen forces that dictate our physical world. Our mission for this deep dive is to take this massive stack of highly technical source material on material failure, fracture mechanics, and fatigue, and just, break it down into the ultimate real-world lesson.
I love it. It's the perfect way to frame it. Because engineering isn't just about building things,
Yeah.
It's fundamentally about predicting how and when things will break.
Right, predicting the failure.
Exactly. Whether you are designing those aircraft engine components, pouring concrete for suspension bridges, laying deep-sea pipelines, or, if you're just insanely curious about why the glass screen on your phone shatters into a spider web while a paperclip can bend back and forth a dozen times before snapping.
Yeah, the paperclip thing is classic.
Right. But the underlying physics are identical. So we are going to dig into the microscopic battlefield inside these materials to see exactly how structural failure happens.
Consider this your orientation, everyone. We have a massive amount of ground to cover. We're going to explore exactly what dictates whether a material stretches like warm putty or violently snaps like a dry twig.
Which is a crucial distinction.
Huge. And we'll break down the silent, insidious killer of engineering structures known as cyclic loading. Then we will explore how engineers actually fight back by intentionally pre-stressing materials to basically cheat physics.
Which is always fun.
Oh, yeah. And finally, we'll zoom all the way down to the atomic lattice itself to see how the literal size of the metal grains changes the physical path of a crack.
And we are going to do it without relying on the dense, unreadable jargon that usually surrounds this field. We want you to understand the why and the how, not just memorize formulas from a textbook.
Exactly. So I want to kick things off with a very relatable observation. Let's say you go into a hardware store, right? And you buy a thick piece of plain carbon steel wire.
Okay, got it.
You take it home, grab it with 2 pliers, and you apply pressure. It slowly bends, it yields to the force.
Right, it deforms.
Yeah. But now you take a stick of standard classroom chalk, you apply that exact same bending pressure, and it doesn't bend at all. There is zero warning. It just, boom, violently snaps in half.
Right, a totally different failure mode.
Yeah, so what is the fundamental, atomic difference between those two materials that causes such drastically different behavior?
Well, it all comes down to their internal atomic architecture, specifically something we call dislocation mobility.
Dislocation mobility, okay.
Yeah. Let's look at the chalk first. Chalk is what we call an ionic solid. The atoms inside it are locked into this really rigid alternating grid of positive and negative charges.
Like a lattice structure.
Exactly. And because of that rigid ionic bonding, there is virtually zero dislocation mobility.
Okay, wait, let's make sure we have a really clear picture of a dislocation for everyone. That's essentially a tiny structural defect, right? Like a missing line of atoms in the crystal lattice.
Precisely. No crystal is perfect. In ductile materials like metals, you have these dislocations, and critically, those dislocations can move.
Oh, they actually shift around.
Yes. When you apply stress to a piece of steel, entire planes of atoms can actually slide past one another along these defects.
Wow, okay.
And this sliding action is what allows the metal to permanently bend without breaking. It's the material's way of gracefully relieving the stress you're putting on it.
But the chalk can't do that.
Right. In an ionic solid like chalk, the atoms are locked down. The internal structure simply cannot slide.
Oh, it's kind of like a massive traffic jam on a highway that's surrounded by concrete barriers on both sides.
Oh, that's a great way to think about it.
Right, because if the cars are packed bumper to bumper and there is absolutely no shoulder to merge into, you have zero mobility. You can't relieve the congestion. So if a truck comes barreling into the back of the line, the force has nowhere to go. You just get an immediate catastrophic crash.
That is a brilliant analogy, yeah. And because the chalk has no shoulder to pull into, because it literally cannot deform to absorb the energy, the primary forces driving the crack are the stresses acting directly perpendicular or, normal to the crack face.
Okay, so pushing straight against it.
Yeah. So if you take a standard cylinder of chalk and you twist it, applying torsion, the principal stresses pulling the material apart are oriented at exactly a 45-degree angle to the axis of the chalk.
Oh, wow. Wait, is that why when you twist a piece of chalk, it always breaks with that weird angled spiral-looking surface?
Exactly. That helical fracture surface is the pure physical signature of a brittle, ionic, solid failing under tension.
That is so cool. I've always wondered why it snaps like that.
Yeah. Now, contrast that chalk with a material on the complete opposite end of the spectrum. Think of something like plasticine or modeling clay.
Right. If I pull on modeling clay, it doesn't snap. It just stretches and thins out until it finally pulls apart into two soft cones.
Exactly, because plasticine is a polymer capable of massive plastic deformation. Its internal structure is completely different from the chalk's rigid grid. It allows molecules to slide past one another incredibly easily.
So it's basically all shoulder, no traffic.
Yeah, basically. So its failure is entirely ductile and occurs via shear. The material literally slides apart.
Oh, interesting.
Yeah. And in this case, the maximum shear stresses act perfectly perpendicular to the axis of the specimen. So you get a flat, sliding failure profile, which is completely different from the angled snap of the chalk.
Okay, that brings us to a massive question that engineers have to grapple with every single day. Obviously, plain carbon steel isn't modeling clay, but it isn't chalk either, right?
Right. It sits somewhere in the middle.
Exactly. So how do we control this? Like, how do we dictate when an industrial material like the steel used in a bridge acts ductile versus when it acts brittle?
Well, we define this behavior using a concept called the ductile brittle transition temperature, or DBPT.
DBTT, okay.
Right. Materials fundamentally change their personality based on temperature. You might have a steel that is wonderfully tough and ductile at room temperature, but if you drop it to freezing, it suddenly acts like glass.
Which is terrifying for winter construction.
Oh, absolutely. But the exact temperature where this transition happens isn't fixed. It is heavily influenced by three main physical pillars, plus the actual physical geometry of the part itself.
Okay, let's break down those pillars. I want to understand this. Let's start with pillar number one, the chemical environment.
This is a huge one, especially for the oil and gas industry. Introducing what we call embrittling agents into the metals environment artificially raises the transition temperature.
So it makes it brittle at higher temperatures than normal.
Exactly. And the most notorious and frankly terrifying of these agents is hydrogen.
Wait, hydrogen, like the most abundant element in the universe. Why is that so dangerous to steel?
Because hydrogen atoms are incredibly tiny. I mean, they're basically just single protons.
Right.
So when a steel pipeline is exposed to certain corrosive environments, or even, during the welding process, these tiny hydrogen atoms can easily diffuse right into the solid metal lattice of the steel.
They just slip right in?
Yeah, they sneak right between the iron atoms. And once inside, they tend to congregate at the tips of microscopic flaws or cracks.
So they basically gang up inside the metal. What do they actually do once they're in there hiding in the cracks?
They interfere with the atomic bonds. It's called decohesion theory. The hydrogen lowers the cohesive energy holding the iron atoms together, and simultaneously, it restricts that crucial dislocation mobility we talked about earlier.
It jams up the traffic again.
Exactly. It jams up the traffic.
Yeah.
So a steel pipeline carrying hydrogen, or one exposed to the deep ocean, will behave as if it's much colder and much more brittle than it actually is.
Wow.
Yeah. It might fail catastrophically under a normal operating pressure simply because it's been poisoned by hydrogen.
That is wild. You can literally poison a metal to make it brittle. Okay, let's move to pillar number two, the strain rate. Now, in layman's terms, this is basically how fast you are hitting the material, right?
That's a great way to put it, yeah. Increasing the strain rate, meaning you apply the physical load, very suddenly increases the transition temperature, pushing the material toward brittle behavior.
Okay, so faster impact equals more brittle.
Exactly.
Yep.
If we connect this back to our traffic jam analogy, it makes perfect sense. Ductile behavior requires those dislocations, those crystal defects, to physically slide and move through the metal to relieve the stress.
Right, the cars need time to merge into the shoulder.
Yes, that atomic sliding is a physical process, and it requires time to happen.
It makes me think of swimming. Or, well, more specifically, slapping the water.
Well, I like where this is going.
Like, if I take my open hand and slowly push it into a pool, the water molecules easily yield and flow around my hand, right? Feels soft.
Right, because you're moving slowly.
Yeah. But if I raise my hand and slap the surface of the pool as fast and as hard as I can, it feels like hitting a sheet of concrete. My hand actually stings because I didn't give the water molecules time to move out of the way.
That is a phenomenal analogy.
Mm.
It is the exact same principle in solid mechanics. If you apply a slow, heavy load to a steel beam, the atomic planes have time to slip. The material bends.
But if it's sudden...
Right, if you hit that exact same steel beam with a sudden, massive, explosive impact, the dislocations simply do not have sufficient time to mobilize in response to the load. The material has absolutely no choice but to snap.
It's all about time. Okay, which brings us to pillar number 3. Alloy composition. What are we actually mixing into the steel in the foundry?
Let's stick with our plain carbon steel example. Increasing the concentration of carbon in the steel increases the transition temperature. It makes it more brittle.
Okay, why does adding carbon do that?
The reason is purely mechanical. Carbon atoms are what we call interstitial, meaning they don't replace iron atoms in the grid. They sit in the empty spaces, the gaps, between the larger iron atoms.
Oh, I see. So they're like boulders sitting in the middle of our highway shoulder.
Exactly. When you add more carbon, you are physically placing roadblocks in the path of the dislocations. The carbon physically pins the dislocations down, inhibiting the motion required for ductile deformation.
So the traffic can't merge at all.
Right. And the trade-off here is legendary in engineering.
Mm.
Adding carbon gives you a much stronger, harder steel that resists bending, but one that is infinitely more likely to shatter into pieces when it finally is pushed past its limit.
It's like a blacksmith making a sword. You want it hard so it stays sharp, but not so hard that it shatters when you hit a shield.
Exactly. It's a delicate balance.
Now, you also mentioned earlier that geometry plays a role. This one confuses me a bit. Why would a thick plate of steel behave differently than a thin sheet if they are poured from the exact same batch of liquid metal?
It is entirely counterintuitive, I'll give you that, until you visualize the stresses. It's the difference between what structural engineers call plane stress and plane strain.
Okay, break that down for me.
Sure. Thick, heavy plates operate under plane strain conditions, and they are significantly more prone to brittle fracture.
Wait, why? Wouldn't thicker be stronger and, safer?
Stronger, yes. Safer against brittle fracture? Absolutely no.
Really?
Yeah, imagine a tiny crack forming deep inside a very thick plate of steel. When the metal right at the tip of that crack tries to stretch and yield to relieve the stress, it can't.
Because there's too much metal around it.
Exactly. It is completely surrounded, boxed in by massive amounts of other solid metal. It can't easily shrink or pull inward in the thickness direction. We call this a triaxial constraint.
Triaxial constraint. Got it.
And because it is physically constrained from yielding, it behaves like our chalk. It snaps.
Oh, but a thin plate has an escape route.
Exactly. For thin plates, you are in a state of plane stress. The size of the deformation zone at the tip of the crack is roughly equal to the thickness of the plate itself.
Okay.
Because the outer surface of the plate is right there, just, millimeters away, the material has freedom. It can yield, pull inward, and physically thin, like striking a piece of taffy to relieve the stress.
Oh, that makes total sense visually.
Yeah, therefore, a failure in a thin plate is almost always going to occur by slow, ductile tearing, giving you plenty of warning, rather than a sudden catastrophic brittle snap.
So when we step back and look at this whole ductile brittle thing, ductility isn't just a magical inherent property printed on a spec sheet.
Not at all.
It's a constant active negotiation between the environment the part lives in, how fast the world impacts it, the chemical roadblocks we've baked into its atomic lattice, and how thick we actually decided to cast it.
Which is exactly why catastrophic failures still happen. I mean, an engineer might design a crane hook perfectly for a static, slow, heavy load in a warm, sunny shipyard.
Yeah.
And it behaves beautifully.
Right.
But take that exact same crane to a freezing offshore oil rig in the North Sea, expose it to a corrosive salt environment, and subject it to sudden swinging impacts from ocean waves. That perfectly designed hook will shatter like dropped glass.
That sets the stage perfectly. I mean, everything we've discussed so far revolves around a single heavy load, like a one-time extreme event.
Correct.
But what happens when we aren't dealing with a massive impact, but rather a tiny, seemingly harmless load applied and removed over and over and over again? That takes us into the realm of the hidden killer of engineering: fatigue.
Fatigue is endlessly fascinating to me because it completely defies human intuition.
How so?
Well, our brains are wired to think, if it can hold 100 pounds once, it can hold 100 pounds forever.
Yeah, that seems logical.
Right. But a steel component might easily and comfortably survive a static, resting load. You hang a weight from it, and it holds indefinitely. But if you take that exact same weight, a load that is mathematically well below the material's yield strength, and you apply it, then remove it, apply it, remove it, thousands of times.
It breaks.
It can and will fail catastrophically,
Yeah.
often with zero visible warning.
I think literally everyone listening has experienced this in real life when trying to break a paper clip or, a zip tie or a piece of wire.
Oh, the paperclip is the classic fatigue test.
Right. You grab it, you pull it with all your might, and you can't break it with your bare hands. It's just too strong. So what do? You bend it back and forth, up and down, maybe 50 times. It gets hot, and then suddenly it snaps with almost no effort.
That is the absolute essence of cyclic loading. And engineers recognized this phenomenon long before we had modern scanning electron microscopes or advanced fracture mechanics.
Really? How far back does this go?
Back in the 1840s and 50s, with the explosion of the railway industry, solid steel train axles were suddenly snapping in half mid-journey.
Oh, man, that's bad.
Yeah, it was disastrous. And these axles were massively overbuilt. By all static calculations, they should have lasted forever. But a German engineer named August Wöhler was one of the first to rigorously investigate this. He developed empirical testing machines, literally rotating bending tests, to figure out why these axles were failing.
So he essentially built a machine to bend giant metal paper clips until they broke, just to track the data.
We did. And to understand what Wöhler found, we need to map out the vocabulary of cyclic loading. We have to define the parameters that characterize a fatigue history.
Okay, let's go.
Imagine looking at a graph on an oscilloscope. The vertical axis is stress, how hard we are pulling or pushing, and the horizontal axis is time. The stress goes up and down in a continuous wave.
Okay, I'm visualizing the wave. What are the specific measurements engineers actually care about here?
The first and most obvious is the stress range. This is simply the absolute maximum stress at the peak of the wave minus the minimum stress at the bottom of the trough. It is the total physical height of the wave.
Makes sense. From the absolute lowest valley to the highest mountain peak, what's next?
Next is the stress amplitude. This is exactly 1/2 of the stress range.
Past the range.
Right. So if your wave fluctuates perfectly evenly around 0, say, you're pulling with 50 pounds of force, then pushing with 50 pounds of force, the stress amplitude is simply 50. It's how far the wave deviates from its center line.
Got it. And then we need to know where that center line actually sits, right? Which I assume is the mean stress?
Correct. Mean stress is 1/2 of the sum of the maximum and minimum stress. It's the baseline that the wave oscillates around.
Okay, give me an example of that.
If you pull on an airplane wing with 100 units of force, and then you only relax it down to 50 units of force, the wave is riding entirely in positive territory. The mean stress in that case is 75. It never goes into compression.
Okay, I follow. And finally, you have the load ratio.
Right, known in equations as R. The load ratio is a quick shorthand. It is simply the minimum stress divided by the maximum stress.
So it's just a quick identifier for engineers?
Exactly.
Yeah.
It instantly tells another engineer what kind of fatigue cycle you're dealing with. If someone tells you the load ratio is -1, you immediately know the minimum stress is the exact mathematical negative of the maximum stress. It is a fully reversed, perfectly balanced cycle.
Now wait, I have to push back here. We've defined the height of the wave, the middle of the wave, the bottom of the wave. But what about the shape of the wave? Or the speed?
Good question.
Like, does the frequency matter if I bend that paperclip back and forth 10 times a second versus 100 times a second? Or what if it's a smooth, gentle sine wave versus a really harsh, jerky square wave? Doesn't a faster, harsher vibration cause more damage?
It is an incredibly logical question, and the answer almost always shocks people when they first learn it. For most structural metals operating at room temperature in a normal, dry atmosphere, frequency and waveform generally do not influence fatigue life.
Wait, really? A cycle is a cycle, whether it takes 1 second or 1 minute.
Purely mechanically, yes. The microscopic damage to the atomic lattice is done by the physical reversal of the strain, the actual sliding of those atomic planes back and forth. The speed at which they slide doesn't significantly change the amount of damage per cycle.
I feel like there has to be a catch.
There's a massive
There-
caveat.
I knew it.
Frequency and waveform become incredibly important, often dominating the failure if environmental effects are present.
The real world ruins the math again.
Exactly. If you are operating a pump in a highly corrosive chemical bath, or in high humidity, or at elevated temperatures like inside a jet turbine where the metal might slowly creep and deform over time, then the clock matters immensely.
Why does the clock matter then?
Because a slower frequency means the crack tip is exposed to that corrosive acid or that extreme heat for a longer duration per cycle. The environment has more time to attack the fresh metal exposed at the crack tip.
Oh, that makes perfect sense.
Right. But if we are testing a steel rod in a perfect vacuum at room temperature, speed doesn't matter. The cycle count is all that matters.
So how do engineers actually use this wave data to predict when a bridge cable or an axle is going to snap? Like, how do they predict the future?
They map it out using what is famously known as an SN curve.
SN curve.
Yeah. S stands for the applied stress amplitude, and N stands for the number of cycles to failure. You plot stress on the vertical axis and cycles on the horizontal axis.
Okay, pretty straightforward.
And because a part might survive 10 million cycles, the horizontal axis is logarithmic, just so we can fit it on a single piece of paper.
So the testing process is basically take a pristine metal rod, hit it with a massive stress amplitude. It breaks in just 1,000 cycles. You log that dot on the graph, take a new rod, hit it with a slightly lower stress. It survives 50,000 cycles. You plot that dot, you keep doing this, and you map out this curve sloping downward. The lower the stress, the longer it lives.
Exactly. You're building a historical map.
But here is the aha moment of this whole field. The curve doesn't just go down forever, does it?
It does not. And this phenomenon is an absolute lifesaver for civilization. For many materials, specifically most plain carbon steels and titanium alloys, as you drop the stress lower and lower, the SN curve eventually flattens out entirely. It becomes a perfectly horizontal line.
And what do we call that?
This threshold is called the endurance limit or the fatigue limit.
And what does a perfectly flat horizontal line actually mean for the physical metal?
It means that if you keep the applied cyclic stress strictly below that specific endurance limit, the component has an effectively infinite life.
Infinite life, literally forever.
From a fatigue standpoint, yes. The micro damage that is created during the loading cycle is so minuscule that it is entirely arrested by the material's internal microscopic barriers, the grain boundaries.
You just stops the cracks in their tracks.
Right. The damage simply cannot accumulate into a fatal crack. The material heals itself, in a way, on every single cycle.
That is incredible. Is there a rule of thumb for where that magical infinite life threshold sits? Like, how much do I have to derate the metal to be safe?
Generally, for steels, this endurance limit hovers around 35 to 50% of the material's ultimate tensile strength.
Okay, so about half.
Roughly, yes. So if your steel alloy snaps under a static pull of 1,000 megapascals, its endurance limit for cyclic vibration will be somewhere around 400 to 500 megapascals. If you keep the vibrations below that, it runs forever.
But wait, do all materials have this infinite life threshold? Because if I'm building an airplane out of aluminum, does aluminum have an endurance limit?
Unfortunately, no. And this is a critical distinction in aerospace. Many non-ferrous alloys, specifically aluminum and copper, do not exhibit a distinct endurance limit.
Wait, they don't?
No, their SN curve just keeps sloping downward, very slowly, forever. No matter how tiny the vibration, if you cycle an aluminum wing enough times, it will eventually crack.
So how do you design an airplane if you know the wings are guaranteed to eventually fall off? That sounds terrifying.
It sounds scary, but it's handled very carefully. For materials without a true endurance limit, engineers arbitrarily define one by convention. They establish a fatigue strength based on a massive number of cycles, usually 10 million or sometimes 500 million cycles for aerospace parts.
Okay.
If the aluminum part can survive a lifetime of flakes that equates to 10 million stress cycles, we deem it safe, and we simply put a mandatory retirement age on the aircraft frame.
Okay, that makes me feel slightly better about flying. So we have these curves mapped out, but engineers can't just stare at graphs all day. They need software, they need math, they need equations to calculate exactly when the part will fail when it's operating on the sloped part of the SN curve.
For that, we rely on the stress life approach, which is governed by the Baskin relationship. Proposed by O.H. Baskin back in 1910, he looked at Willers's data and realized that if you plot the logarithm of the stress amplitude against the logarithm of the cycles to failure, that curved line straightens out into a perfect diagonal line.
Let's translate this math into concepts, because reading raw equations on a deep dive is a great way to put people to sleep. How does this relationship actually work? What is the spoken math here?
Let's keep it conversational. Baskin's relationship basically maps out a balanced scale for survival. The equation is basically delta sigma divided by 2, which gives us the stress amplitude. And that equals the material's fatigue strength coefficient multiplied by the quantity 2 times NF, all raised to the power of B.
Okay, so on one side of the ledger, you have your stress amplitude, how hard you are bending or pulling the metal.
Right. And on the other side, you have the material's innate fatigue strength coefficient, which is basically its true strength in a single massive pull scaled by the number of times you're cycling it, which is the NF part.
And the crucial part is that the number of cycles is tied to an exponent, right? That back you mentioned, the Baskin exponent.
Exactly. Because it's an exponential relationship governed by that Baskin exponent, it means fatigue is incredibly sensitive to the load.
How sensitive.
Extremely. A tiny 10% increase in the stress you are applying doesn't just reduce the part's life by 10%. It might slash the number of cycles it can survive by half or more. It drops off a cliff.
So if I know my metal's baseline strength and I know its specific exponent, which tells me how steep that cliff is, I can plug in my operating vibration and know exactly how many days or hours the part will survive.
That is the foundation of high cycle fatigue design.
But as I'm about to point out, this perfectly mathematically predictable world only exists in a laboratory where the loading is perfectly balanced around 0.
Oh, absolutely.
Exactly. The laboratory tests assume you pull with 10 pounds, then push with 10 pounds. Mean stress is 0. But real life is messy. What if the suspension bridge cable is already pre-tensioned to hold up thousands of tons of concrete, and then the wind starts vibrating it? The cable is constantly under tension. The resting state isn't 0.
Right. And pulling a material tight before you start vibrating it drastically accelerates fatigue failure. The mean stress is non-zero and usually positive. To account for this, engineers over the decades developed mean stress correction models.
How do they work? Do they just artificially lower the endurance limit?
Essentially, yes. These models take the safe stress amplitude you calculated for a perfectly balanced test, and they penalize it. They shrink your safe operating window based on how much static mean stress is constantly sitting on the part. There are 3 famous historical models used for this: Soderberg, Goodman, and Gerber.
Let's walk through them. Let's start with Soderberg.
The Soderberg model was developed for the paranoid engineer. It is incredibly conservative.
Paranoid engineer, I like that.
It essentially says that as your static mean stress climbs closer to the material's yield point, the point where it starts to permanently bend, your allowable safe cyclic vibration drops in a straight, shear line down to 0.
So it's super strict.
Very. If you are resting at the yield point, you cannot tolerate any vibration at all.
Better safe than sorry, I guess. But if I'm building an airplane, better safe than sorry means the plane is so heavy with extra metal that it can't take off.
Exactly. Soderberg often results in parts that are unnecessarily bulky. So the aerospace and automotive industries often turn to the Goodman model.
How does Goodman give us more breathing room?
Goodman is less conservative. It uses a very similar linear penalty, but instead of drawing the line down to the yield point, it draws a line all the way out to the ultimate tensile strength, the point where the metal actually rips into 2 pieces.
Oh, that's a big difference.
Yeah, because the ultimate tensile strength is much higher than the yield point. The Goodman model gives the engineer a much larger envelope of allowable vibrations to work within.
So it's a bit riskier, but it saves weight. What about the third one, Gerber?
The Gerber model throws out the straight line entirely. Experimental data, particularly for highly ductile alloys under tension, show that the failure points didn't drop in a straight line. Right.
They
bulged outward in a curve. So Gerber uses a parabola to map the penalty.
A curve gives you even more operating room in the middle ranges.
It does, and it's highly accurate for tensile mean stresses. But there is a mathematical flaw in the Gerber model.
What's the flaw?
Because the formula uses the square of the mean stress to create that parabola, a negative mean stress, meaning the part is under constant compression, becomes positive when you square it. The mass penalizes you for compression.
But wait, earlier we said squeezing a crash shut is good.
Exactly. Compressive mean stresses are incredibly beneficial and actually extend fatigue life. So the Gerber model is physically wrong for compressive loads. You should never use it if your part is being squeezed, only if it's being stretched.
Okay, so we've solved for unbalanced loads. We know how to penalize the math. But here is the ultimate real-world problem. If I'm driving a heavy 18-wheeler truck over a steel bridge, sometimes the truck is fully loaded with cargo, maximum stress wave.
Right.
Other times, the truck is totally empty, minimum stress wave. Sometimes it's a calm day. Sometimes there are massive crosswinds. The bridge is experiencing wildly different amplitudes of stress every single minute of the day. It's a totally chaotic history.
It is chaos.
So how on earth do you add up the different amounts of damage to know when the bridge will collapse?
This is perhaps the most critical challenge in structural engineering, quantifying cumulative damage. The universal standard, despite its flaws, is the Palmgren-Minor linear damage rule.
Palmgren-Minor. I love the concept of this because it's so intuitively simple. Walk us through how we calculate the damage.
It's brilliantly simple. It relies on fractions. Imagine a steel component.
Yeah.
From our SN curves, we know that if we subject it strictly to a high stress, let's call it stress level A, it will snap at exactly 10,000 cycles.
Okay.
Now, in the real world, the part only experiences 1,000 cycles of stress level A before the load changes. What have you done? You have consumed exactly 1/10 or 10% of its total life.
Right. A simple fraction. 1,000 divided by 10,000.
Correct. Now the wind dies down. The load drops to stress level B. At this lower stress, the SN curve says the part could normally survive 100,000 cycles. Our real-world part runs for 20,000 cycles at this lower level.
So 20,000 divided by 100,000, that's 20%. You've consumed 20% of its life at the lower stress.
Exactly. Palmgren-Minor simply tells you to add the fractions. 10% from the high stress plus 20% from the low stress. You have consumed 30% of the component's total fatigue life. You keep monitoring the loads, adding up the fractions.
And when do you hit failure?
When the sum of all those fractions reaches 1 or 100%, the math says the component breaks.
It is elegant. It's perfectly linear. But you said despite its flaws, what is the catch? Does the order of the loads matter? Like, what if the truck is heavy on Monday and light on Tuesday versus light on Monday and heavy on Tuesday?
That is the massive fatal flaw of the rule. The Palmgren-Minor equation inherently assumed that the sequence in which the loads are applied has absolutely zero influence on the outcome.
Which mathematically makes sense. Addition is commutative.
Right, 10 plus 20 is the same as 20 plus 10. But in the physical reality of metallurgy, the sequence of loads matters immensely.
Let's explore that. Give me a physical example of how the sequence changes the survival of the metal.
Let's take case 1. High stress first, low stress second. You apply a massive violent cyclic load to a pristine part. Because the stress is so high, it easily initiates microscopic cracks at the surface of the metal.
Okay, damage is done.
Then you lower the load. Now you are applying a gentle low-stress cycle.
But the cracks are already there.
Precisely. That gentle low stress might never have been strong enough to initiate a crack on its own. But because the high stress already opened the door, the low stress is perfectly capable of propagating those existing microcracks.
Ah, I see.
A crack physically concentrates the stress right at its impossibly sharp tip, so the damage accelerates rapidly. In this high-low scenario, the part will fail much earlier than Palmgren-Minor predicts. The sum of the fractions might only reach 0.7 before the part snaps.
So the math says you have 30% life left, but the part is already broken on the floor. That's terrifying. Now let's reverse it. Case 2, low stress first, high stress second.
In case 2, you apply the gentle low-stress cycle first. It isn't high enough to cause any microcracks. But what it does do is manipulate the internal lattice. It causes dislocations to move and tangle up around each other. We call this strain hardening.
Chain hardened.
Yes. The surface of the metal actually becomes physically harder and stronger.
It's literally like an athlete warming up, conditioning their muscles before the heavy lift.
It's a perfect analogy. The metal is conditioned. Then, when you finally apply the massive high-stress load, it is attacking a material that has been hardened by the previous cycles.
So it puts up a better fight.
It is now significantly more difficult for that high stress to initiate surface damage. In this low-high scenario, the part actually lives much longer than the math predicts. The Palmgren-Minor sum might reach 1.5 before failure.
So the history, the actual lived experience of the metal fundamentally alters its future.
I love that. Now, speaking of the lived experience of the metal, Everything we have discussed so far assumes the metal is staying mostly elastic. It's springing back to its original shape like a
Okay.
rubber band.
Yes, mostly elastic.
But what happens when we push the material so violently that it deforms permanently on every single cycle? It doesn't spring back, it yields.
That brings us to a massive fork in the road for engineering design. High cycle fatigue versus low cycle fatigue.
Let's define the boundary.
Huh?
High cycle fatigue is what we've been talking about, right?
Right.
Correct. The stress life approach, Wöhler's curves, Baskin's relationship, these are all built for high cycle fatigue, or HCF. They apply to situations where the stresses are relatively low, the deformation is almost entirely elastic, and you expect the component to survive tens of thousands or millions of cycles.
But sometimes a component is subjected to absolute hell. I'm thinking of the turbine blades inside a jet engine experiencing massive thermal expansion, or the metal around a sharp bolt hole in an excavator bucket.
In those extreme situations, significant plasticity is involved. The material isn't just springing back, it is physically yielding. It is stretching and compressing permanently, back and forth, on every cycle.
That sounds rough on the metal.
It is. And when this happens, the component's lifetime is going to be incredibly short, maybe just a few hundred or a few thousand cycles. This is low cycle fatigue, or LCF.
And I assume our beautiful stress life equations completely break down here.
They collapse entirely. Stress is no longer a reliable indicator of the damage being done.
Why not?
Because once a metal yields and goes plastic, a tiny, almost unmeasurable increase in stress causes a massive sweeping increase in physical strain. You can't track the stress accurately anymore.
So if we can't measure the invisible force, the stress, what do we measure?
We measure the physical reality. We use a strain life approach. Rather than characterizing the fatigue load by stress amplitude, we measure the plastic strain amplitude. We track exactly how far the material is being physically stretched and deformed beyond its elastic limit.
And there is a mathematical model for this, similar to Baskin.
Yes, developed in the 1950s, known as the Coffin-Manson relationship. Rather than using the material's innate strength, Coffin-Manson acts as a balance scale, using the material's innate ductility.
Okay, give me the spoken math for that one too.
Sure, it's delta epsilon sub e divided by 2, which gives us our plastic strain amplitude. And that equals epsilon prime f, which is the fatigue ductility coefficient, multiplied by the quantity 2 times nf, raised to the power of c.
So on one side, you have the physical plastic strain you are inflicting. On the other side, you have that fatigue ductility coefficient, essentially, how much the metal can stretch like taffy before tearing scaled by the number of cycles to failure.
You've got it perfectly.
So we have two competing universes. Baskin rules the high cycle universe, governed by the strength of the metal. Coffin-Manson rules the low cycle universe, governed by the ductility of the metal. How do engineers bridge the gap?
Through the strain life general approach, it's wonderfully logical. Total physical strain is simply the sum of elastic strain plus plastic strain.
Makes sense.
So the total strain amplitude equation just combines the two. The elastic portion, governed by Baskin, added to the plastic portion, governed by Coffin-Manson.
If you plot both of those curves on the same graph, do they cross over?
They do. They intersect exactly at what we call the transition life. It's the physical point where the elastic damage and the plastic damage are exactly equal.
What does that crossover point actually mean for an engineer choosing a material to build a machine?
It represents a brutal engineering reality. If your part needs a long life, if you are operating well past the crossover point in the high cycle regime, the elastic strain is completely dominant. Therefore, the strength of the material controls its performance. You want a hard, ultra-strong metal to survive.
But if I'm building something that only needs to survive 100 massive violent impacts,
Then you are operating before the crossover point in the low cycle regime. Here, plastic strain dominates the damage. The ductility of the material controls its performance. You do not want a hard metal. You want a soft, forgiving, ductile metal that can stretch and absorb the energy without instantly tearing.
and here's where I see the cruelest irony in all of material science.
It is a profound irony. In almost all engineering alloys, any thermal or chemical process you use to increase the strength of the metal leads directly and unavoidably to a reduction in its ductility.
And vice versa, you cannot have both.
You really can't.
So if I take a piece of steel and heat treat it, quenching it in oil to make it incredibly strong,
It will perform flawlessly in a high-cycle fatigue environment, like a high-speed motor shaft. But if you put that same hardened steel into a low-cycle environment with massive yielding strains, it will shatter instantly.
Nah.
Conversely, if you anneal the steel in a furnace to make it soft and highly ductile, it survives low cycle fatigue wonderfully, but fails rapidly under high cycle vibration. You have to choose your weapon and your material based entirely on the expected lifespan and operating environment of the part. There is no master key.
That is incredible. Okay, so we know how cracks start, we know how they grow, and how the inherent properties of the metal dictate its survival. But how do we actively fight back? Like, how do we stop the cracks before they even begin? Let's talk about cheating physics. How do engineers deliberately pre-stress materials to save them?
To understand how we cheat, you have to understand the fundamental law of fracture mechanics. Cracks generally will not initiate, nor will they propagate, in a compressively stressed zone.
Meaning what, exactly?
Meaning cracks need tension to open up. Think about a crack in a piece of plastic. If you pull the plastic apart, the crack opens and tears further. But if you squeeze the plastic together, the crack is forced shut. It can't grow.
Oh, obviously.
So the holy grail of fatigue prevention is to induce a permanent state of residual compressive stress on the outer surface of a component.
So the goal is to permanently squeeze the outside layer of the metal so that even when the machine is running and pulling on the part, the net force at the surface is still pushing inward, keeping the crack shut.
Exactly. You beat the tension by starting with compression.
A great real-world example of this, something literally everyone listening interacts with daily, is tempered glass, the screen on your smartphone or the windshield of your car. How does tempering actually create this residual squeeze?
Tempering is a brilliant thermomechanical process. Let's look at a car windshield. You take a sheet of ordinary brittle glass and heat it in a furnace until it's soft, glowing, and able to flow. Then you blast both the outer surfaces with high-pressure jets of cool air.
So the outside skins of the glass drop in temperature immediately.
Right, because they cool rapidly, they contract, shrink, and solidify into a hard, rigid shell. But remember, the thick inner core of the glass is still glowing hot and thermally expanded.
Right, the heat is trapped inside.
As the outer shells shrink, the hot core just flows and squishes along with them, offering no resistance.
But eventually, thermodynamics wins. That hot inner core has to cool down to room temperature too.
And that is the trap. When the inner core finally cools, it attempts to shrink and contract. But it is now permanently fused to an outer shell that is already cold, rock hard, and rigidly set in its dimensions. So as the core shrinks, it pulls fiercely inward on the outer shell.
It's dragging the surface inward, which puts the core into a permanent state of tension, pulling itself apart, but it puts the outer surface into massive, permanent residual compression. It is squeezing itself from the inside out.
Precisely. And this is vital because when glass is loaded in tension, like when a rock hits, your windshield failure almost always initiates from microscopic flaws on the surface. But for tempered glass, before the impact force can even begin to exert a tearing, opening load on those surface cracks, it must first completely overcome that massive, built-in compressive squeeze.
It's like having a heavy-duty rubber band wrapped as tightly as possible around a block of wood. Before you can pull the wood apart, you first have to pull hard enough to defeat the squeeze of the rubber band. That's why tempered glass can sustain such massive impacts before shattering.
Yes, and we use the exact same concept on metals. But obviously, we can't always heat and rapidly cool complex massive metal geometries like an engine block or a turbine blade the way we do flat glass.
Right, that would warp everything.
So we use a mechanical process. We use a brute force. It's called shot peening.
Shot peening. I absolutely love this concept. It sounds aggressive. It literally involves bombarding a critical metal part with millions of tiny spherical media called shot, like sandblasting. But instead of cutting sand, you use little metal, glass, or ceramic balls.
That's a perfect visualization. You fire these tiny spheres at high velocity. Each piece of shot striking the surface acts like a microscopic high-speed peening hammer. When it impacts the metal, it imparts a tiny, shallow indentation or dimple into the surface.
And what does that microscopic dimple do to the metal underneath?
When the shot hits, it stretches the top layer of the metal plastically. It yields the metal right at the point of impact, forcing it to spread outwards, like dropping a bowling ball in mud.
Okay.
But the thick bulk of the material underneath hasn't been hit. It hasn't yielded. It is still perfectly elastic. So the bulk underlying material acts like a giant spring, trying to push that stretched, dimpled surface layer back to its original size.
So the top layer wants to be bigger. The bottom layer is forcing it to stay small. The net result.
The net result is a highly uniform, dense layer of material at the surface locked in a permanent, powerful state of residual compression. It is identical to the tempered glass. Typically, the residual compressive stress produced by shot peening is at least half the yield strength of the material being peened.
Half the yield strength. That's a massive, invisible protective shield built right into the metal. Where is this actually used in the field?
Everywhere that fatigue is the primary mode of failure. Aerospace relies on it heavily. The titanium blades, buckets, and discs inside a jet engine are intensely shot peened.
Just to handle the vibrations.
Yeah, the blade roots, where they attach to the hub, are peened to prevent fretting, galling, and fatigue from the insane rotational vibrations. You find it on the crankshafts of heavy diesel trucks, automotive gear transmissions, marine drive shafts.
Oh, wow.
They even use a variant called peen forming on the massive aluminum wing skins of passenger aircraft. By selectively bombarding one side of the flat aluminum, they can gently curve the metal into the aerodynamic shape of a wing while simultaneously bulletproofing it against fatigue.
And hitting the metal with millions of tiny hammers doesn't just create compression, right? There's a metallurgical bonus effect.
Correct. It also provides intense cold working of the surface. Just as we discussed earlier with strain hardening, massive plastic deformation causes the dislocations in the metal to tangle up and lock together.
So it's double protection.
Yeah, this cold working significantly hardens and strengthens the surface layer, providing drastically better resistance against wear, intergranular corrosion, and it even physically hammers shut microscopic porosity in cast metal parts.
It is just a brilliantly elegant engineering solution. Use brute force to induce a squeeze that stops cracks from breathing. Now, we've been talking about macroscopic structures, jet engine blades, car windshields, suspension bridges.
The big stuff.
Yeah, but to truly understand material failure, I want to zoom all the way in. Past the dimples, past the surface, what does a crack actually look like when it travels through the atomic lattice itself? Let's dive into the microscopic battlefield.
To set the stage here, we need to correct a common misconception. Metals are not just uniform, homogeneous blocks of matter. They are crystalline.
Okay.
When liquid metal cools and solidifies in a foundry, it forms microscopic crystals called grains. These grains grow outward until they bump into one another. The borders where the different crystals meet are called grain boundaries.
Okay, so let's set up a theoretical scenario based on the latest metallurgical research. We have two samples of the exact same metal alloy. The first is what we call a nanocrystalline material. The average grain size is incredibly small, almost unimaginably small, say just 40 nanometers across.
Very tiny.
The second sample is a microcrystalline material where the grains are much larger, say larger than 1 micrometer. That's a huge difference in scale. How does a fatigue crack behave differently as it tries to tear through each of these structures?
The difference is striking, and it dictates the toughness of the metal. It all comes down to how the crack tip interacts with those grain boundaries. In the nanocrystalline material, with the ultra-tiny 40 nanometer grains, the path of the crack under simple cyclic tension is perfectly linear. It is undeflected. It acts like a laser beam.
It just cuts straight through. Why? It doesn't hit the boundaries?
It does, but the grains are so unimaginably tiny relative to the plastic zone at the tip of the crack that the material effectively acts as a homogeneous, continuous solid. The crack simply slices straight through the macrostructure. It doesn't see the individual grains as structural obstacles because they're just too small to deflect the massive energy of the crack tip.
But what happens when we move to the microcrystalline regime, where the grains are 50 or 100 times larger?
Now, the crack encounters massive, distinct crystal boundaries. And remember, each grain has its atomic lattice oriented in a slightly different direction.
Oh, so the grid changes direction.
Exactly. When the crack reaches a grain boundary, it can't just slice straight across. The weakest atomic planes in the new grain are pointing in a different direction. The crack has to physically reorient itself to follow the path of least resistance through the new crystal lattice.
So the crack is forced to turn. This is what researchers call crystallographic crack path deflection.
Exactly. The crack literally zigs and zags. It tilts and twists three-dimensionally as it navigates the maze of crystal boundaries.
Now, I can visualize that, but does this actually slow the crack down? I mean, geometrically, it has to travel a slightly longer total distance because it's zigzagging instead of going in a straight line. But is there a physical, mechanical benefit to the deflection?
Yes, a massive one. It's not just about the distance. When the crack deflects and tilts away from the primary plane of stress, The effective stress intensity at the very tip of the crack is mathematically reduced.
Let me make sure I understand. Because it turned a corner, the main force pulling the part apart isn't pulling directly on the tip anymore.
Exactly. The force driving it forward is diluted because the tip is no longer pointing directly into the main tensile load. It's pulling at an angle. It loses efficiency.
That's incredible. So a larger grain structure is actually a natural defense mechanism against crack growth.
It is, and the zigzag in geometry induces a secondary defense mechanism known as roughness-induced crack closure.
Roughness-induced closure. What does that mean physically?
Because the crack path is so jagged and tortuous, the two faces of the crack aren't perfectly smooth mirror images anymore. During the unloading part of the fatigue cycle, as the metal tries to relax, those jagged, mountainous edges actually rub against each other. They wedge together behind the crack tip, effectively propping the crack open.
Wow, so the jagged edges act like a doorstop.
Yes, they physically shield the tip of the crack from experiencing the full range of stress during the next cycle. It absorbs the energy. So larger grain structures, in the specific context of crack propagation, physically slow down fatigue failure by forcing the crack to take a tortuous, energy-draining path and wedging itself shut.
I absolutely love that visualization. A crack desperately trying to navigate a microscopic maze of crystal boundaries, losing momentum and energy with every single turn.
That's a great image.
But as fascinating as that is, to truly predict these failures in the real world, especially when we push materials into extreme disaster scenarios where they are yielding, stretching, and tearing on a massive scale, we need the heaviest mathematical artillery in all of engineering.
And that brings us to our final topic, elastic plastic fracture mechanics, and the infamous J integral.
To truly appreciate the genius of the J integral, we have to look back at the historical limitations of early fracture mechanics. In the mid-20th century, we had the Williams solution and linear elastic fracture mechanics. These relied on a parameter called K, the stress intensity factor.
Okay, K?
But K came with a massive restrictive assumption: small-scale yielding. Small-scale yielding, meaning the little zone of plastic, permanent deformation, right at the very tip of the crack, has to be absolutely tiny compared to the overall size of the steel beam or part. The vast majority of the part has to remain perfectly springy and elastic.
Right. If the part is massive and the crack is tiny, K works beautifully.
Right.
But what happens in a real-world catastrophic failure? Or what happens when you are testing modern, highly ductile, super tough metals?
That plastic zone isn't tiny.
It can be massive. The metal is visibly stretching, flowing, and tearing far beyond its elastic limits long before it finally snaps. When this large-scale yielding happens, the linear equations behind K completely collapse. They produce garbage data.
Enter Professor J.R. Rice, 1968.
Yes. Professor J.R. Rice, alongside brilliant related work by researchers like Cherpanoff, Eshelby, and Sanders, revolutionized the entire field by introducing the J integral. It is a mathematical and thermodynamic tool specifically designed for situations where there is massive large-scale yielding.
Let's unpack this conceptually. How does it work? I know from the literature it involves drawing a mathematical path, or a contour loop, around the crack tip.
Exactly. The J integral is a path-independent line integral. Mathematically, you draw a line starting from the lower face of the crack, looping counterclockwise entirely around the chaotic plastic zone at the crack tip and ending on the upper face of the crack.
In simple physical terms, what is this integral actually measuring inside that loop?
Physically, it represents the rate of change of the net mechanical potential energy with respect to crack advance for a nonlinear elastic solid. But to put it much more simply, it is a direct measure of the energy flowing into the crack tip from the surrounding material.
Ah, so it's tracking the energy.
It tells you exactly how much juice is driving the crack forward, even when the surrounding metal is permanently yielding and warping.
You said earlier it's path independent. Every paper on the subject highlights this. This is the superpower of the J integral. But what does path independence actually mean for an engineer standing in a testing lab?
It is nothing short of a mathematical miracle. Path independence means that the equation yields the exact same answer regardless of how close or how far away you draw your integration path from the actual crack tip.
Wait, really? Explain how we use that.
Let's say you have path 1. It tightly hugs the microscopic tip of the crack, right in the heart of the plastic zone where everything is chaotic, atoms are sliding, heat is being generated, and it is physically impossible to attach sensors to measure the stress accurately.
Okay, an impossible measurement.
Then you draw path 2. Path 2 is a massive loop drawn far away from the crack, way out on the outer edges of the metal block in the elastic region, where the stresses and strains are smooth, predictable, and incredibly easy to measure with standard, cheap strain gauges.
And the math of the J integral guarantees that the energy flowing through the massive, easy-to-measure path 2 is exactly equal to the energy flowing into the microscopic, chaotic path 1.
Exactly. The energy is conserved within the contour. J calculated along path 1 equals J calculated along path 2. This allowed engineers, for the first time in history, to accurately determine the catastrophic conditions at the microscopic crack tip by taking simple, large-scale measurements far away from the tip.
That is utterly brilliant. It's like calculating exactly how much water is draining out of a microscopic hole in a sink by measuring the gentle flow of water at the edges of the basin. Now, this doesn't just sit in a vacuum. It connects back to the older linear models, doesn't it?
Yes, it is fully backward compatible. The G integral is formulated using deformation theory of plasticity, which is essentially equivalent to nonlinear elasticity. Because of this, it forms a perfect bridge. For the special case of a perfectly brittle, linear, elastic solid like our chalk, or high-strength glass J, is mathematically exactly equal to G, the strain energy release rate.
Why is that equivalence so important practically? I mean, why did this save the testing industry?
Because of test specimen size requirements. To accurately measure the fracture toughness of a highly ductile metal using the old linear K methods, the standards dictate that the specimen has to be unimaginably massive to enforce that small-scale yielding rule.
How massive are we talking?
If you wanted to test the toughness of a low-strength steel used in a submarine hull using linear methods, the required solid block of steel might need to be over 1 meter thick.
1 meter thick. You'd need a testing machine the size of a building just to pull it apart. It's physically impossible and absurdly expensive.
Exactly. The industry was hitting a wall, but with the J integral.
Because J can handle large-scale yielding without breaking a sweat.
Exactly. The specimen size requirements for a J test are exponentially less severe. You can take a highly ductile steel, machine a small, deeply cracked, compact tension specimen, maybe just 1 inch thick, put it in a standard lab machine, measure the critical J value at failure, and then use the mathematical equivalence to back-calculate what the equivalent linear toughness value would be.
That's genius.
It literally saved the entire field of fracture testing from structural and economic impossibility.
Wow. We went from requiring a block of steel the size of a refrigerator to something you can hold in your hand, all because J.R. Rice proved the energy flow is path independent. Okay, one final concept here to wrap up the physics. If the metal is stretching so much under this large-scale yielding, if the J integral is working so hard, the crack itself isn't just a microscopic, mathematically sharp line anymore, right? It must physically deform.
Absolutely. The mathematical concept of a sharp crack tip breaks down in reality. And this brings us to a physical measurement called CTO, the crack tip opening displacement.
Crack tip opening displacement.
Yeah. Because of the massive plastic deformation happening at the tip, the crack literally blunts. Before the crack actually advances forward and tears new metal, the tip stretches and opens up into a U shape.
So you can physically measure how far the jaws of the cracks stretch open before they snap.
Yes. The strict definition is slightly arbitrary since the opening width varies as you approach the exact curved tip, so engineers use an operational definition, often based on a 45-degree construction line drawn from the crack tip back to the crack faces. But the critical takeaway is that this CTOD is used as a direct physical measure of the material's toughness.
Like a visible gauge.
Exactly. It is an experimental visual measure of the driving force behind the fracture. The more a crack tip can blunt, stretch, and yawn open without actually advancing forward, the tougher and safer the material is.
It's the material desperately trying to absorb the energy by stretching its jaws rather than letting the crack rip forward. This has been absolutely phenomenal, from the macro world of airplane wings down to the atomic lattice. As we wrap up this masterclass, do you have a final provocative thought to leave the listener with?
I do. Think about everything we've covered today. From the tiny, invisible hydrogen atom sneaking in and embrittling a steel pipeline, to the zigzagging, tortuous path of a crack navigating a microcrystalline lattice, all the way to the mathematically perfect, path-independent J integral, capturing the massive energy flow of yielding steel.
It's a lot to take in.
It is. Our physical world, the materials we build our civilization with, are a constant, invisible battleground of energy. The next time you look at a suspension bridge, a skyscraper, or the spinning jet engine on an aircraft, don't look at it as a piece of static, dead metal. Look at it as a living, dynamic system. It is constantly fighting against the microscopic forces of fatigue, desperately holding on to its residual compressive stresses, relying on its grain boundaries to deflect damage, just to survive one more cycle.
What a profound perspective. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.